Hello and welcome everyone. So we are starting in on a new unit. Some of you may have already seen the first part of the slide. I'll make sure and put a little annotation to tell you where you can jump to in the video. But also I wanted to put this up here so that way you can take your notes on it, for future purposes, your quizzes and your next test. It's going to be open notes as well. And as with this last test, a lot of the information I'm going to be pulling straight from the slides. So it is really in your best interest to take good notes. We are talking about the engineering design process, or EDP. The big idea is that the EDP is systematic and an iterative problem-solving method. And so the fact of that, it means that we're going to be repeating what we're going to do a lot. And so just, what do we mean by iterative? And it's repetition of a process. So in math, there are certain iterative calculations that happen in math where you just, you compute the number and then you're going to compute it again and then you're going to compute it again. And in some systems, you do that multiple times. In science, some of what we're talking about, just really not just science, but just about anything, is you're going to go through kind of like a trial and error process. That's an iterative process. Or sometimes you just have to do things multiple times. In baking, something that actually I just worked on this weekend was you have to kind of mix up a dough, let it rise, punch it down, mix it up again, let it rise, and you have to do that a couple of times. All of these are examples of iteration where you just go through the process multiple times. Same process or similar process multiple times. The key thing for us with the EDP is that each time you go through the design process, you think of ways to improve the solution or the problem based off of the performance or based off of the testing. And so our iterations are not to just necessarily reach a goal, but to improve upon it in each time. As I've said in some of the other classes, when we use the term fail or failure, in this context, what we're talking about is that it doesn't work right. And you're going to see that a lot in your work, at least initially. And so part of this iteration is to try and get it to work right, and also to get it to work into a more acceptable standard. So it may work, but just barely. And so we want it to where it works consistently. And so we try it again and again. And that's what we mean by iteration, or that it is iterative. So we also took just a few minutes, again, these are slides that we've already covered, into just defining science, defining technology. They're really one and the same. I mean, the acronym STEM is science, technology, engineering, and math. And part of the acronym is that you can't really have any single element without the others. Just like the word STEM doesn't really mean anything unless you have the other letters in it as well. And but engineering, science, technology, math, they're all kind of part of the same thing. But let's define this a little bit further. Science is systematic knowledge of the physical or natural world that is gained through observation and experimentation. It focuses on the how and the why that things happen. And the scientists are there to answer these kind of questions that come up. Why does something operate the way it does? And technology is the application of that knowledge. And so you use the science to gain the knowledge, and the technology takes that knowledge and then does something with it, like solve practical problems or change and manipulate the human environment. The focus, instead of just answering questions, is to make things happen. And sometimes the technology is used to make the science happen. So it comes back on itself. And it is the engineers that solve these problems to use in the quote unquote, to use in the real world. The scientific method it's a little bit more of a linear method, and the thing about it is that it has kind of a start, it has a finish, and so there is an end goal that you're trying to reach, and it goes through this process: make an observation, propose your hypothesis, design an experiment, test the hypothesis, accept or reject the hypothesis, and then revise the hypothesis or you end the experiment by drawing the appropriate conclusions. You're still going to draw the conclusions even if you go back and revise your hypothesis, but it wouldn't necessarily be the immediate end. Whereas the engineering design process, the EDP, is this continual thing. It keeps going, even on products that have been out for a very long time. There's still advancements that can be made. There's still things that can be done to improve. And it systematically applies the math and the science to produce tangible products. And there's a delicate word there, tangible, because there are certain things that exist, like a book is a tangible object that would come through, but it's the content of the book which is not necessarily tangible that you're talking about. And some of that information may come through with ideas like EDP. So we have to keep in mind that while these definitions, they use particular words because it conveys the bulk of the ideas. Almost all the time when we're talking about EDP, we're going to be talking about something tangible, but there are still times where we might venture outside of that idea. So, and just be okay with that. But for the most part, this definition is going to be working fine. When we first started this course and we mentioned the EDP, we talked about it in these 5 steps. But as the problems become more complex, so does the process to solve them. If we were to sketch out all of the steps, you might see cycles within cycles and loops within loops and different elements if you try and track it out. And we have ways of keeping all of this in check, but it will still revolve around these 5 basic ideas. So no matter how complex it gets, somewhere within that problem, you'll still be able to see these 5 major points. So moving into some of the more complex ideas, we're also breaking down these broader terms, such as brainstorming ideas. Brainstorming ideas can mean a lot. So we're breaking these down into smaller subcategories that may or may not, that we may or may not have to go through. Defining the problem. Brainstorming ideas, we have brainstorm possible solution, and research. Research your ideas to explore possibilities. When you start exploring what the solutions are, you need to look at, specify what are the constraints and other identifying criteria. Look into alternative methods. If there's something that already exists that works, that meets your needs or meets part of your needs, use that instead of designing it from scratch. Once you decide on what you're doing, that's selecting an approach. Develop a written design proposal. That is something that we have not quite done yet. But it is something that's very necessary because, in a true design process, you've either A, got somebody who is funding you, or B, you're trying to get somebody to fund your project. And so you need to have something that they can review to see where they need to go. Make a model or a prototype. In some of our projects so far, we haven't done anything like that. But in a major construction, you're gonna see these kind of things. Test and evaluate, refine and improve. You test it, you see what works, what doesn't. You refine it to try and get more stuff that works and less stuff that doesn't. And then finally, you get into that create or make the product. Again, most of the time, which is going to be very tangible. Okay, so here's a quick exercise that you can do. Pause the video and then determine which of these terms belong in the scientific method and which of these belong in the EDP. Okay, so I'm going to move on. And so there's the answers to the problem if you tried that exercise on your own. But you can kind of, if you did this, you can kind of get a little bit of a feel. They're very similar. They're very similar, and that just the scientific way of thinking, whether you're talking about science, whether you're talking about math or engineering or technology, they all have their similarities. So now here's something that we haven't been doing a lot when it comes to the EDP. Use the Engineering Design Journal to record each step in the EDP. Something that we are going to introduce in the next component is a design journal. When we start documenting different things that go into play, we're going to look at other things like making a timeline and various other various tools that are used. But you want to record every step, including the failures. The failures are going to teach you more than any amount of getting something right. So you want to record everything that you're doing, and I mean, to the point that for a lot of us, it's going to seem almost like obnoxiously critical. But even something like switching to a different brand of nail if you were building something can potentially make a difference, and that is all sorts of documentation, different kinds of documentation that you're going to need. Define the problem. Develop a problem statement that identifies the what, who, when, and how the problem should be addressed. Again, this is another one of those, the more you document, the better that you're going to be. Because you, as the person who is documenting what the problem is, may not actually be the person who is solving the problem. So anything that you believe is going to be relevant to, that's going to be relative to solving the problem needs to be documented. And all of the classic questions, who, what, when, where, and how, and why. The more of those that you can address, the more of those that you can answer when defining the problems, the better that you're going to be. The problem statement should be short, descriptive, and reference as you work through the EDP. So, don't write a novel. Write enough information. If it can be said in 10 words, use 10. Don't use 8. If it can be said in 10 words, use 10. Don't use 20. Try and find, you want to use the bare minimum that adequately describes the problem, but yet completely describes the problem. When you're brainstorming your solutions, when working as a group, record your ideas and employ the rules of brainstorming. One conversation at a time, stay focused. We have a tendency to get off topic. There's nothing wrong with getting off topic. But as an engineer, you're going to be working under time constraints. And so the more off topic you get, the less time you're going to have to actually do your work. But now here's something that's a little bit different. Wild ideas are acceptable. And there's story after story of these just kind of crazy ideas off the wall that actually ended up working. And then the second is this quantity versus quality. This is always going to be something that you have to address. I'm not going to give you, explanation as to why, but for the purposes of this course, I am more about quality. I want to see that you're doing good work rather than fast work. And defer judgment and build on the ideas of others. This is the, there are no stupid questions kind of scenario. If you don't like an idea, we have a tendency when somebody gives an idea that isn't something we were already thinking, we tend to argue against it just because it wasn't our ideas. But when you listen to others, they may have really good ideas, and either they may have an idea that helps build on yours, or you may listen to their idea, take what you were already thinking, and find ways to build upon theirs. And you end up with a much better overall product. And by product, it could be tangible, it could be theoretical, than if you just try to do this on your own. So just examples of brainstorming, there's mind mapping, Da Vinci method, or inventive problem solving, and as well as a myriad of other techniques that you can use. Researching your ideas, exploring the possibilities. Research is essential to determining the best possible solution. We all have our ideas. If I said, okay, build a bridge using toothpicks and glue, we all probably have an image that automatically pops up into mind. And the short answer is, if I give a series of particular constraints, and everybody comes up with a different idea, only one of them will be the best. And so it's using research, and most likely it's going to be a blend of everybody's ideas that is truly the best. And that's where the research comes in. You get a lot of people working together. Everybody puts in their input. You weigh the pros and cons, and eventually you can work out a more adequate solution. Identify how the problem or a similar problem was addressed in the past. In the case of building a toothpick bridge, how has it been done previously? Is it something that you can do? Don't just necessarily do a one-for-one copy, but you can use it to kind of influence your design. Determine what mathematical or scientific background knowledge is essential to solve the problem. In engineering school, you started off, freshman math in college was calculus. And if you were not starting off in calculus, then you were already behind. And so then you had to take multiple math classes to catch up. And it was a challenge because in engineering, at least at NC State, you had a math every semester. So you had to double up on your math if you didn't start off in calculus. But calculus was not used in every single problem that we ever encountered. It was used in some of them, but not in all of them. So just because you have certain knowledge doesn't mean that that knowledge is appropriate for that problem, and always be mindful of that. Specify the constraints and identify the criteria. Good design follows a set of given or identified criteria or constraints. The criteria, those are your guidelines. You know, I want you to build a bridge. I want you to build a bridge. It has to meet a certain set of conditions, and that would be some of those criteria. The constraints, you need to do it using only 500 toothpicks. Okay, that's all you get. And if you break them, that's all you get. Real world, a lot of the constraints are money or time. I need it done within a certain period of time, and those sort of things. Sometimes what one person may call guideline is another person's constraint, but there is a slightly different. Guidelines are general rules. Constraints are an absolute must. Document the essential criteria and constraints needed to solve the problem. What is the must-haves, and then everything else is extra. So the bridge needs to be functional. It needs to hold a certain amount of weight, no matter what. Does it look pretty? It doesn't have to, but it would be nice if it could, and that's extra stuff that comes in later. Consider alternative solutions. Always consider the alternative solutions, and do not allow preconceptions to limit your ideas. This is tough. Do not allow preconceptions to limit your ideas. As a teacher, I hear all the time, and it's challenging for me sometimes when somebody gives out an idea to just go, you don't like it, so you just go, it won't work. It won't work. But now you'll be surprised at how often that they do. And that's one of those. There's always a little bit of a balance. I can tell you right now, you can't put enough firecrackers under a metal can to get it to launch up into space. It just can't be done. There are laws of physics that say even if you got enough, it's still not going to be able to be done, because long story short, the weight of the firecracker, the more weight that you add to the firecracker, the less efficient it is, and eventually you reach a point where you have so many firecrackers, it weighs more than the firecrackers themselves can lift. That's it. So there are some things that just won't work. But when you're talking about ideas, it's always good to listen to others, because even if it turns out that the idea itself won't work, there might be things about that concept that you didn't think of that you can incorporate into your design. And so that hits our next bullet point. It's important to stay open-minded about these things. Some of the best and highest profit yielding inventions weren't revolutionary inventions. They weren't something that was so far out there that nobody ever it took an Einstein or a Stephen Hawking or an Isaac Newton to come up with it. It was just something that was very local, very available, and it just, nobody had happened to invest in the idea enough. You know, nobody thought of it. And my personal favorite on that one is the George Foreman grill. Electric grills, the electric hot plate griddle style devices had been around for a long time. George Foreman, or his company, however that fully transpired, just put it at an angle. And it became, and you know, there was a period of time when everybody had a George Foreman grill, and it was just something so simple. And but you know, if people had been closed off to that idea, it never would have happened. Compare each of your designs with the criteria and the constraints to determine how well they solve the problem. This is that collaboration. A team of people working together is always going to do better than the individual. Always. That's it. End of story. So you need to be comfortable working with other people. And if you're not, for those of you who are shy, talk to me. I can, you know, try and help. That's part of my job. And for those of you, if you just, you know, I just don't like that person, that's not acceptable in this class. You're going to have to learn to work together, because there's always going to be somebody on your team that you don't like. It always happens. I've taught for a long time, and there's always that one person that I'm just like, man, I wish that they weren't on my team. But inevitably they're there. I can tell you as a teacher, there's almost always, at least one semester, there's always at least one student where I'm like, oh, I wish they weren't in my class. But I still work with them, and you know, and you would never even know that I didn't like that student. So teamwork is going to be critical here. Select your approach. Determining the best solution will involve trade-offs. I like that they put the best here in quotations, because it may not actually be the best, but it may be the best that you have come up with. And the key word there, trade-off. There's almost, you know, it's very rare in engineering that you're going to get a best solution that works for everything and for everybody. The best solution should align to the problem statement, where, you know, we already defined the problem. And it should meet the identified criteria and constraints. If it doesn't if it doesn't meet both those bullet points, it's not the best. I don't care how good it looks. I don't care, you know, in the bridge building exercise, if the weight was that it was supposed to hold 5 pounds, I don't care if it could hold 500 pounds. If it falls outside of any of these two criteria, it's still not the best. End of story. No questions asked. Use a decision matrix to help identify the best solution. A decision matrix is something that we kind of have those ideas in our brain, but we've never really, you know, well, I won't say we never, but we may not have actually written it out in this format. A decision matrix is a simple way to chart your proposed solutions against the requirements. X-axis, those what create the column, what create the columns that run on the x-axis. Those are your ideas, you know, idea 1, 2, and 3. And then what run in the y, or what run in the rows, are the different constraints that you know, that, and then you just kind of score it. You just kind of score it. Which one meets the constraints the best, which one meets the criteria the best. And you can actually put a numerical value in this, and we'll practice this some. We will practice this one some. And you know, and these will obviously at some point end up with right or wrong answers. Now, do you have to set it up specifically this way? And of course the answer is no. The answer is no. What is important is that you keep the ideas in one section, either the rows or the columns. You don't mix them in both. And the problems and the constraints and the criteria, same thing. You keep those grouped together. They can either be, in this case they're in the rows. I could have put them in the columns as long as I don't have it mixed. Because then the total, you know, you're going to have a total in here somewhere. So we'll work with those for a little bit. Develop a written design proposal. So once you've gone, let me back up for a second. Look at all the work that is going into this before you ever truly get into designing and prototyping. When people think engineers, they think design and prototype. And look at how much work we're covering before we ever get into actual prototyping. Okay? Develop a written design proposal. So what it's going to look for all of you is that once I give the problem, Once you kind of make your decision, then you write a design proposal and then you send it to me. And me not knowing what you're doing, because I might actually, I've got some teachers that I've teamed up with, I might actually hand it to them and go, what do you think? Could you follow their instructions? Could you follow their design proposal? And if they say yes, it's good. If they say, I don't know what they're talking about, then that's very bad. Once an idea has been selected, it's important to develop a plan of action. The design proposal is a way to manage simple projects, and you can use a design proposal to manage complex problems as well. But you would have one overlooming design proposal within the several subsequent smaller design proposals. The who, what, when, where, and how to deliver the work. We're going to be bringing in a new idea of when. We've got time constraints now. This often includes descriptions, sketches, and technical drawings. We're going to talk about how to do technical drawings. I've already introduced some of the basic ideas behind sketches, but we're going to build on those. And then begin to plan out how the solution will be evaluated. Okay. In the case of the bridge, can it hold 5 pounds? Yes. If it doesn't, it fails. But in the case of something else, like something close to home for me, is designing an airplane. Does it fly? Yes. Does it reach a particular fuel efficiency? Yes. Then good. But no, then we need to go back and redesign because it uses too much fuel. Stuff like that can change how you evaluate the object that you're working with. When developing a design proposal, you will need to plan to determine how you will evaluate your design, what tests will be conducted to determine if the criteria is being met. Again, with the bridge, you're going to test, does it hold the 5 pounds? And if it does, great. If not, then no. How will the data be collected? So you can't just say, yeah, it held 5 pounds. You have to be able to say, well, we filled up put 5 pounds worth of Matchbox cars on the bridge and did it that way. Because another thing is there's something called point load and distributed load. 10 cars, one behind the other on a bridge weighing 5 pounds, and again, let's assume Matchbox cars or something like that, is going to act much differently than those same 10 cars stacked on top of each other and then set in the middle of the bridge. So that is important information that you need to collect. And then how will those data be used to improve the solution? So this gets into what happens if it fails, or there's a possibility, well, if you were able to design it to hold 5 pounds, could you design it to hold 10, and so on. Larger projects may require the use of a project management technique or a Gantt chart. So that is this beneath here is an example of a Gantt chart, and we'll look at those. Ours will not be for this class. We're probably going to rely a little bit more into just reading these kind of charts, whereas if you take the subsequent classes, you'll actually have to make these kind of charts. But a Gantt chart is a type of bar chart that shows the schedule of how and when the project can be completed. And there is something in math called a critical path, which all involves reading these kind of charts, and you're trying to find the optimum amount of time. Because if you say, Mr. Andrews, I think we can get this project done in 10 days, 10 days, not 10 business days, then at the end of 10 days, you better have it ready. And so the Gantt charts help you determine how long that's going to be. Make your model or your prototype. So I've used this term. It can be conceptual, mathematical, or physical. Mathematical models, if you were designing a sphere, you can actually do that using just math, and that's okay. There are some things I mentioned before, modeling how birds fly. You're not necessarily going to go into a science lab and release 200 birds, but you can make a mathematical model that simulates on a computer how those birds would operate, and that is something that will work, and that's another way that you could represent it. Or you could fly 200 paper airplanes and hope that they fly like birds. That would be an example of a physical model. Okay. Conceptual models are abstract. That can use language and graphic-based representations to convey meaning. So these are this is actually a lot of what you did with the backpack project. Is in a way you created like a PowerPoint, and so that kind of borderlines here in this graphs and charts, because they can include technical writing, graphs, charts, annotated sketches, technical drawings, lab reports, things of that nature all fall into this. So just by making a model or prototype doesn't necessarily mean you have a physical object to hold. Mathematical objects are abstract models that use language and mathematics to describe their behavior and solution. They can include statistical models, differential equations. That's what I was talking. I mentioned earlier about solving problems using problems that only a computer could solve, such as how does heat distribute through a certain material. Statistical model, looking at standard deviation, mean, median, and mode. And game theoretic models. Game theory is a very interesting realm of mathematics. And what I will say, for those of you who think that it sounds interesting, I mean, it really is interesting. And there's some really cool things that happen because of game theory, but a mathematical game is not what you think of. You're not going to take a game theory class and be playing Halo and Call of Duty. You can use game theory to model some things if you were in a contest using, playing those video games. But game theory is something entirely different. And in fact, one of the ones that I found most interesting in game theory is inheritance settlements. So yes, in mathematics, an inheritance is a game. Okay, so again, it's a weird thing, and I'm more than happy to talk to you about it. Also, Mr. Lowen is a great resource for that one as well. Physical models, three-dimensional models that can represent the solution. They don't always have to be 3 dimensions, but since we live in a 3D world, three-dimensional models are best. They can include mock-ups, representation of the final solution. It does not function, so you can build a car that does not work at all, but it gives people an idea of where you're going. Or the prototype. Performs the final solution, can be used for testing and evaluation. Mock-ups are very popular in the future, something that we can't do right now, very, very unfortunately. I'm looking into a program where you would design your own house. And so a mock-up would be a 3D printed house. But very unfortunately, we're not going to be able to do that because we all have to physically be on campus. I'll have to check. I'll talk with Ms. Jones because I did just have a thought. So I'm going to write that down as soon as I pause the video. Test and evaluate. Project planning and evaluation go together. I've already mentioned that, where the idea between the testing, the evaluation, all of that are in a way they're almost one and the same. They're two sides of the same coin, would be one way I would describe it. Based on the information you projected in your design proposal, you will record and analyze your results. We put the 10 cars on the bridge, and it did not break, but it did bow over here, so we need to reinforce that structure. It did not bow over here, and we thought it was going to bow. So when we reinforce that structure, we need to see what's going to happen. By bow, I mean bend. And correct the problems with the design that are discovered during testing. Hey, it bent over, in section A. We thought it was going to bend in section B. What's going on? Refine and improve. Employ data-driven decision making. Data-driven is a very hot buzzword right now. Look at what your results are telling you and use it to decide what to do next. Use the data collected during the test and evaluate phase to justify improvements to the solution. Sometimes there may be no improvements, but that is going to be very, very rare. When it gets to, as we continue further on in the semester, there will be practically no time when I say, yep, that's fine, and then just leave it at that. I will be putting out in constructive criticism some things that you could do potentially to make it better. not because I'm trying to be mean, but because I want you to get used to being in that mindset of consistent improvement. You can always improve. Doesn't mean you're bad, but we can always improve. And that's just true for human beings in general. The solution should be continuously improved as you move through the EDP. Okay, I just said that. You know, you should always be willing to improve. Remember to document all of your project improvements in your journal. If you change anything, it needs to be documented. Create and make the product. Working independently or in a group, develop the final physical solution. The final solution should represent the revision made as you followed the EDP. The product should clearly reflect the refinement made to the design throughout the process. So it is possible that your final product look absolutely nothing like the original design in your design proposal. I'm going to say that again. It is possible that your final product does not look anything like your original design. And that is okay. Because as you have gone through each iteration and as you have been making these adjustments and changes and switches, you've also been in communication with everyone that needs to know and are explaining what's happening, because it may turn out your initial assumption had some fundamental flaws in it that needed to be addressed. That kind of stuff happens, and it's okay. This is what I mean when I said at the very beginning, failure will happen. You started off, hey, Mr. Andrews, we have this idea. You start working on the idea, Mr. Andrews, we need to change parts C, D, and E. And so you change parts C, D, and E. Mr. Andrews, we need, next iteration, Mr. Andrews, we need to change part M. Okay, let's change it. Mr. Andrews, we need to change this part. And before you know it, it doesn't look like your original one. But that's not a failure. That is not a failure at all, because you were consistently improving. Just because it looks different doesn't mean that what you did was wrong. I'm going to say that again. Just because you end up with something different than what you had in the beginning doesn't mean that you did anything wrong, okay? It's all right. And for some of you, it may happen in full, but there's going to be a lot of you, it didn't finish the way you thought it was going to at the beginning, and it's okay. That's okay. That's part of this class. It's just growing with it. Okay. Use the EDP journal to record and document each step of the engineering design process. This is communication. This is communicating the results. If you told me, Mr. Andrews, we're going to bake you an apple pie, and then the day that you were going to bring in the pie, you come in with a chocolate cake, I might be a little bit, I might kind of go, wait a second, this isn't what you promised. But as I look at what was done, Mr. Andrews, we tried to do an apple pie, but all the apples were rotten. Okay, well, thank you for not bringing me a rotten apple pie. I would greatly appreciate that. You see, and that's the purpose of the engineering design journal, and that's the purpose of that communication. If I knew right off the get-go all the apples are rotten, then I would say, don't bring me an apple pie. Well, Mr. Andrews, we still want to do something nice for you. How about a cake? Okay, sure. You see, and just like that, you went from there being a potential problem with change to a very acceptable and reasonable change. A more formal presentation or demonstration of the solution may be required, which should summarize the work, includes problem statement, design problem, evaluation methods, etc., etc., etc. Okay, we will have at the end of the semester a formal presentation. And so that's where Powtoon, Flip Grid, all of these things are really, they're going to come back, they're going to come into play. Evaluation methods, design proposals, we're going to be looking into using things like Tinkercad to help create some of this stuff. Highlight why you chose the final solution. Did it meet all the criteria? Were you happy with it? Was there something that you wish you could have changed? And you know what? That's possible. That's possible because we're also operating under a time constraint. But ultimately, why did you go with plan A instead of going with plan B? Why did you go with plan S instead of with plan M, N, or O? That needs to be explained. Okay? So this is a lot of information. And it's stuff that we're going to be dealing with in chunks as we go throughout the rest of the semester. I hope that you enjoyed this video, and I look forward to hearing some of your thoughts and explanations and just seeing where the rest of this course carries us. Thank you, and have a great day.